Now going to talk about a couple of subjects that aren't always covered in texts that cover the Laplace transform. One is using the Laplace transform to evaluate certain definite integrals. Remember, this is, well, if you have an integral in this form, limits are 0 to infinity, and e to the minus at times the function. This almost looks like the Laplace transform, except it's got this a constant, instead of s. You have the s, the complex variable, if this were the Laplace transform. So this would just be then that Laplace transform evaluated at s equals a, right? So the Laplace transform of a function of this, so if you put in a for s, it's the same thing. So the Laplace you can evaluate this integral by finding the Laplace transform of this f and plugging in a for s. Let's do a couple of examples. So say you have this equation or this integral. Oh, and somebody's using x instead of t. It doesn't matter. It's a variable of integration. We integrate the x out of it. So it makes you comfortable. I can put t back in for x. And this is just the Laplace transform of t, evaluated at s equals 1. There's not an s here, there's just 1. Laplace transform of t is 1 over s squared. When I plug in s equals 1, I just give you 1. How about this guy? In fact, by the way, this comes in handy for some probability distributions. A lot of times they involve an exponential like this. So let's say this. Now it's not just x, but x to some power. Make us comfortable. Plug in t for x, t to the n. This little Laplace transform of t evaluated again at s equals 1. This is in our table. Here's the answer. How about this? Oops, this looks tricky because the limits of the integral don't match. It's from minus infinity to infinity. But if you notice, that's an even function and that's an even function. We haven't talked about that yet, but this is the same. It's the same for positive and negative x. So we could multiply by 2 and just integrate from 0 to infinity. Same thing. Get rid of that absolute value sign. So here now we can look it up. This is a is now 2, and the time function is t squared. Still have the 2 out in front. So there's the 2 out in front. The Laplace transform of t squared evaluated at s equals 2. T squared is in the table. Plug in 2 for s. It's a half. What if I have a function of 2 variables like this, x and y? I'm integrating over x. Well, I just treat y as a constant in that case. I'll change it, my variable to t, to make it look familiar. And this is the Laplace transform of t evaluated s equals y plus 1. So now instead of just substituting in a constant for s, I'm substituting in y plus 1, and I get this as my answer. Because for this to work, s has to be greater than 0, so y plus 1 has to be greater than 0. Y is greater than minus 1. So that's one thing. Now we'll introduce linear systems theory. And I won't go through how we model such things, but this little situation here, if you know what the truck is doing, trying to figure out what the cart's going to do, it has a mass, it's attached to the truck, a spring and damper that are considered linear with known coefficients. It ends up with this differential equation. or this differential equation where I put all the y stuff on one side, which is the displacement of the cart, and all the f stuff on the other side, which is the displacement of the truck. And this happens a lot in systems theory, that there's a lot of physical systems that can be modeled by good old linear differential equations like this is here. Let's look at this equation. If we're going to use these assumptions here, we start at rest and in equilibrium. That means all the variables and their derivatives are 0 at time 0. So we can take the Laplace transform of this equation term by term, where every derivative is just multiplying by s. And because we're starting at rest, all those initial conditions are 0. So when we use that property of a derivative, all we got to do is multiply every derivative by s. So this will be s squared times big Y. So we got all the Y stuff on the left. So I've got a big Y here, m times s squared plus b times s plus k. And over here, I'll have a b times s plus k. With the y over the f, I have this thing. If I divide everything through by m, I have this. We call that ratio the transfer function. Consider f as the input and y as the output. This transfer function tells us how to get the output for a certain input. We'll get the output, take the transfer function and multiply it by the input in the Laplace domain. So that g is called a transfer function. So if you have any two of these three, you can find the other one. If I have input and output, I can find the transfer function. If I have the transfer function in the input, I can get the output. Or if I have the transfer function in the output, I can get the input. What if that input, f whatever it is the impulse, the Dirac delta function? Well, the Laplace transform of that is just 1. So this output is this product, but f now is just 1, so the output is just g. So the output in the time domain is the inverse Laplace transform of the impulse function, little g. So I have the output. This is the relationship between output, transfer function, and input. And what it means is, in the time domain, the output is the convolution of f and g. That's what that means, or this, either way, since convolution is unitive. So GT then is called, in this context, it's called the weighted function. You can also find the output by taking this integral, this convolution. E weight function input. So this little g, it's kind of two things at once. It's the weighting function in this context where you take an integral, and it's also the inverse Laplace transform of the transfer function. I'll just skip. There's some more properties. I'll leave it there for a second. Whoever it's, but I won't go through the derivation. If this limit exists, what's the function of time as time goes to infinity? Well, one way to find it is to find the Laplace transform, multiply it by s, and take the limit as s of that as s goes to 0. So you can do something in the Laplace domain, and it tells you something in the time domain. The limit, we'll call that steady state as t goes to infinity. If these limits exist, it's this limit as s goes to 0. So anyway, a few subjects that are a little bit above and beyond normal Laplace transform material. That's the end of Laplace transform.